Welcome to everyone. I am Dr. K.S.Rangasamy, Professor, Department of Mechanical Engineering, K.S.Rangasamy College of Technology. Today I am going to deliver a lecture on fluid properties. The course name will be 50ME005 Fluid Mechanics and Fluid Machines. So before we enter into the subject, we must know what is meant by fluid. So generally we have defined matter is existing in three phases. We know that solid, liquid and gas. At very high temperatures, the matter will also exist as a plasma. The word liquid and gases, the substances in the phase of liquid and gases are termed as fluid. The distinction between solid and fluid is made on the basis of substance ability to resist applied shear stress. Shear stress is also mentioned as tangential stress that tend to change the shape of the solids. We know that solid will resist any type of forces applied onto it, especially the shear stresses. It will resist initially. After that, it will be starts to deforming. Right? Whereas fluid, it will deform continuously under the influence of shear stress, no matter how small the applied shear stress is. Right? The fluid will deform continuously. This is the original definition of fluid. In generally, we define the fluid as the substance that can flow, but actually, be a technical person, we should term the fluid as the substance which deform continuously under the action of shear force. No matter how small we are applying the shear force. For a small 0.1, if you apply 0.1 Newton meter of Newton of shear force, it will deform continuously. So in solids, the stress is proportional to strain. We know the Hooke's law. In solids, Hooke's law is defined as the stress is directly proportional to strain up to elastic limit. But in case of fluid, the stress is proportional to the strain rate. Right? When a constant shear force is applied, a solid eventually stops to deforming at the some point strain angle. Whereas in fluid, it will never stop the deforming and approaches a constant rate of strain. So this is the major difference between the fluid and solid. So fluid is a substance, it will deform continuously under the action of small, even a very, very thin amount of shear stress, it will deform continuously. Right. Next, we will discuss about fluid mechanics. We know the term called fluid, and we know the term mechanics. So mechanics is a study of any body which are at rest and motion. That is the mechanics. If you combine it with fluid, it will term fluid mechanics. So we have to study the behavior of fluid at rest or in motion. So fluid at rest is termed as fluid statics. The fluid at motion is termed as fluid dynamics. Right? So fluid mechanics can be divided into three categories. The static is referred as hydrostatics. For dynamics, it refers as kinematics and fluid dynamics. Right? So hydrostatics deals with the study of fluid at rest or motion in a constant velocity, moving at a constant velocity. In kinematics, it's study of geometry of fluid motion. So here geometry means we have to know the velocity and acceleration, displacement, velocity and acceleration. That refers to the kinematics of fluid flow. In dynamics of fluid flow, we are going to study the forces that cause the accelerated motion. Right? So in kinematics, we will deal with the study of fluid behavior respect to geometry. We are not going to consider the forces acting on the fluid flow. But in fluid dynamics, we have to refer the forces which causes that motion. That's a major difference between kinematics of fluid flow and dynamics of fluid flow. Next, we will discuss about the fluid properties. So first property for any fluid is referred as density or mass density, denoted by rho. Right? So density is generally referred as the amount of mass in a given volume. How much amount of mass for a given volume of any body or any fluid is packed, right? For example, if you take a brick, it is higher density than a sponge because the particles are more tightly packed. If you take a sponge of same size and a brick of same size, the brick holds the higher density and then sponge holds the lower density because the density where the packing of the brick is very high when compared to the sponge, right? So density is referred as mass per volume. The unit of density will be kilogram per meter cube. The standard density of water is 1000 kg per meter cube at 4 degree Celsius. So this is very very important. For a mercury it is 1300 13,600 kg per meter cube. Then olive oil 920 kg per meter cube. Now we will study the interaction of density with respect to temperature and pressure. If you increase the temperature, density will decrease. If you increase the pressure, density will increase for any fluid. So fluid property, that is density, is a function of pressure and temperature. For example, if you increase the temperature, the intermolecular distance between the fluid particle will be increases so that the density will loses. So, in pressure, if you increase the pressure, the intermolecular distance between the two atoms will be increased so that the density of the fluid will decreases or increases. So, pressure increases, the density also increases. So, here pressure and density are indirectly proportional, so directly proportional. In temperature and density are indirectly proportional. Temperature is indirectly proportional to density. Here pressure is directly proportional to density. This is what we have to know. The next term is specific volume. So it is defined as volume per unit mass of the fluid. Generally, if you take density and specific volume, so specific volume is reciprocal of density. You can see here in density we are referred as mass per volume. But in specific volume, volume per mass. So reciprocal of density is called as specific volume. So next, specific weight denoted by gamma. So specific weight is nothing but weight per volume, right? So density is nothing but mass per volume. Specific weight means weight per volume. The weight we can take as mass into gravity, acceleration due to gravity. So this mass per volume we referred it as density rho, then gravity g. So the specific weight may be termed as density into specific gravity. For fluids we have to know the specific weight is very very important. As far as solids we go with density, but as far as fluid we go with the specific weight. Then specific gravity. So specific gravity is a dimensionless number where we have to take the ratio of density of given liquid to the standard liquid. For liquid we take water as a standard liquid. For gases we take air as a standard gas, right? So it's nothing but the ratio of two densities. We have to compare the density of given liquid with a standard liquid. In case of liquids we take in water as a standard liquid. For in terms of gases we have to take air as a standard gas, right? So specific gravity is nothing but ratio of densities. Then viscosity. So viscosity generally it is termed as resistance to shear stress or any liquid. It is referred as resistance to flow. That means the major viscosity is due to the cohesive and molecular momentum between the fluid layers. In case of liquids, for example, in case of oil or in case of water, the cohesive forces between the molecules is responsible for viscosity. In terms of gases, if you take air or oxygen or any type of gases, the molecular momentum transfer between the gases is responsible for viscosity. So as far as viscosity is concerned, cohesive forces plays a major role as far as liquids are concerned. Then molecular momentum plays a major role for viscosity of gases, right? Then the viscosity of liquids decreases with increase in temperature, whereas in gases, the viscosity increases with increase in temperature. This is what the two terms we have to know about the viscosity, how it behaves with respect to increase in temperature with the liquids and gases. For example, if you take ideal fluid which has no viscosity, but in practical cases we cannot say there is no viscosity. For every fluid, we will have some amount of viscosity. If the viscosity is very very small, then we may be termed as ideal fluids. But in practical case, no such fluids are exist. But for our reference, we termed it as ideal fluid. Then we will see about cohesion and adhesion. Cohesion is nothing but the molecular attraction between the same molecules. For example, if you take water, the water droplet, the shape of water droplet is due to cohesive forces because it will enables a liquid to resist the surface tension. Right? The cohesive forces are intermolecular attraction between the same substance. Whereas adhesion, it's an intermolecular attraction between the different substance, right? So intermolecular attraction is different. Intramolecules, for example, if you take a water in a container, the container walls will wetted by the water because of this adhesion, right? So it's an intramolecular attraction, but cohesion is intermolecular attraction. So these both cohesion and adhesion plays a major role in surface tension and capillarity. Okay, well, next we will discuss about surface tension. It is denoted as sigma. This is mainly caused by the molecular cohesion, right? So it is measured as the force per unit length acting on a liquid surface, right? So surface tension becomes smaller as the temperature rises. For example, if I take this molecule, these lines are representing the intermolecular attraction between the two fluid. For example, if I have another layer this, then it will be attracted towards all direction, right? So these both molecules are attracted towards each other, then resultant cohesive force will be zero, right? If you take this molecule which is on the surface of the liquid, this is called the free surface, right? Free surface of liquid. If you take this surface, the you can see the two forces acting. For example, if I take another substance here or another molecule here, there are some resultant cohesive forces on the vertically downward direction. See here, these forces will be balanced each other, but what about these forces? It will create a tensile force on the fluid surface. That tensile force divided by unit length is referred as surface tension. Right? A layer, top layer or free surface of the any fluid will have some tension due to this cohesive force. Those are unbalanced forces on the surface of the any liquid, right? See, it is also referred as surface energy per unit area, so denoted by Newton meter per meter square or joule per meter square. So surface tension also referred as energy, surface energy per unit area. So for any liquid, it value depends primarily upon the temperature. So higher temperature, the more thermal agitation occurs, the surface tension becomes smaller, right? So next one, capillary effect. So capillary effect is nothing but rise or fall of the liquid in a small diameter tube. So that small diameter tube is referred as capillarity tube. Right. So capillarity liquid depends upon the comparison between forces of adhesion and cohesion. For example, if you take wetting liquid, especially this is a water, if you take the adhesion of molecules on the surface of its container is greater than the forces of cohesion. So adhesion is greater than the cohesion, then the liquid is rises on the walls of the tube like this. You can see the liquid is rises, right? So this is due to the adhesion force is greater than the cohesive force. But if we take mercury, right? The adhesive force of mercury is less than the cohesive forces of that mercury, so that the mercury will fall on the container surface like this. Here the water is raised, that's why it is called as wetting liquid. The here you can see the shape of the water is convex, sorry, concave, convex shape on the mercury. So here concave shape on water, right? So this is concave shape, this is convex shape. This shape is due to the cohesion and adhesion between the particles. So this is capillary effect. Both surface tension and capillary effect is due to the cohesive and adhesive forces. So this part wetting liquid is called capillary rise, and this part is left